Noah, are you? Whoa, why is it all wet in here?
Oh, hey, Pete. I'm just getting ready for the show.
Well, it seems like you're getting ready to head out to sea. What's going on?
Oh, not much. I just set up this inflatable pool so Ducky and I can practice our diving etiquette.
Your diving etiquette? Well, I gotta tell you, it doesn't seem very genteel to be splashing water all over the studio.
Well, I'll have you know, Pete, that I am a gentleman. A gentleman and a diver.
I think you mean a gentleman and a scholar.
No, I mean a gentleman and a diver. Check out all my scuba gear. I've got a mask and a tank and everything. Oh, and these really cool flippers. They're pretty hard to walk in, though.
Okay, what's that around your neck? Is it a bow tie?
It is a bow tie. Pretty classy, huh? A real gentleman, I am.
Dude, what are you talking about? We're supposed to be recording in like 5 minutes, and you're dressed up like Captain Scuba and talking like Bert the Chimney Sweep.
But, Pete, we're doing a show about divergence. I'm getting into character.
Divergent?
Yeah, like scuba divers, but with really good manners. A couple of real gentlemen.
Noah, the show is about divergence, as in Divergent series, like from calculus. There's no scuba diving.
There's no scuba diving?
Nope, none.
But, well, what about the gentlemen?
Also nope. It's just you and me.
Oh, man. I rented this tuxedo wetsuit for nothing.
You do kind of look like a penguin.
Dude, that's not funny. It was expensive.
Yeah, that's a real bummer, but hey, do you think we can, like, record the show now?
Okay, fine. Come on, Ducky. Let's go dry off.
Oh, and take your time. We'll just wait here until you're ready.
Are you ready, kids?
Aye, aye, Captain!
I can't hear you.
Aye, aye, Captain!
Oh!
Okay, Pete, I think I'm ready to go. And I hear you. We're talking about divergence, not divergence. But what is a divergent series?
Yeah, so a divergent series is... Well, here, let me illustrate this with an example that kind of comes to mind, something that happened to me just about 10 years ago. I was working at Amazon, and I showed up for work one morning, and there was a lot of buzz going on in the room next to mine. So I poked my head in to see what was going on, and all of the engineers that are in there are talking like really animatedly about this mathematics result that they had seen on some video. I said, well, what's going on, guys? And they said, well, would you believe if I told you that 1 plus 2 plus 3 plus 4 all the way up adds up to negative 1/12? And, you know, of course, like, no, I'm not, I definitely don't believe you.
You're unbelievable.
But that's what they were talking about. And so that's what we're going to talk about, is the kind of divergent series that sort of blow your mind when you see the claims that people make about them.
Okay, so to make sure I understand this right so far, your coworkers were watching a video that claimed that if you add up all the positive whole numbers, 1 plus 2 plus 3, all the way to infinity, the total that you would get after adding all of these numbers up is negative 1/12. Is that what they were saying?
That's exactly what they were saying. And, you know, so everybody was just giggling and sort of shouting and arguing and trying to figure out what that could possibly be.
Well, I can kind of get behind their disbelief, because how can you possibly add up a whole bunch of positive numbers and get an answer that's negative? That doesn't make any sense. And not only an answer that's negative, but an answer that's a tiny little negative number, like negative 1/12. How could that even happen?
I know, you know, that's the part that I think is the funniest about this, is that the answer is negative 1/12. When, you know, clearly it should add up to infinity, right? There's no way it should be something negative. And why this weirdo answer of negative 1/12? But let's take a step back and talk about the kind of series that this is an example of, these so-called divergent series. And I think even before we do that, we should probably mention what a convergent series is. In other words, what kind of series are opposite these so-called divergent series.
Okay. Can you give us an example?
Yeah, so these are the kind of series that are going to be very familiar to anyone who's taken calculus. You have an infinite sequence of numbers, and let me give you an example. 1 plus 1/2 plus 1/4 plus 1/8, and so on. You can see the pattern there. It's 1 divided by a power of 2. And you want to know, what does this sum of numbers add up to? Or more precisely, where is this sum headed in the sense of a limit in calculus? And sometimes you'll write down a series like this one that goes somewhere. This one approaches the value of 2, and we would say that series converges to 2. But not every series does converge to any finite number, even if the series doesn't look crazy, like 1 plus 2 plus 3 plus 4, and so on. So calculus students spend a lot of time looking at different types of series and trying to figure out, do they converge or do they diverge? And if they converge, what is their limiting value? What is their sum, as we say?
I think I remember talking about this particular series before in one of our earlier episodes. Didn't we talk about this exact same series in our episode about Gabriel's horn?
We did. And I think we gave it as an example of a convergent series. And, it's actually a really important one. It's an example of a so-called geometric series. Let me tell you the form of a geometric series real quick. So if I pick some number, let's call it R. I'm using the letter R for ratio. Let's say I want to look at 1 plus R squared plus R cubed and so forth, and ask the question, does this tend to a limit? And now the series that we're talking about here uses the value R equals 1/2. So it's 1 plus 1/2 plus 1/2 squared plus 1/2 cubed and so forth. So you could use negatives here. If the absolute value of the ratio is less than 1, then the series converges. And in fact, the answer is 1 divided by 1 minus R. So if we set R equal to 1/2, we end up with 1 divided by 1/2, which is equal to 2.
So when we talk about a convergent series, we basically mean it's an infinite series. And when you add up all the terms in that series, they get closer and closer and closer to some specific limit without ever getting there. Is that what we're saying?
Yeah, essentially that's it. The partial sums are heading to a limit. And what I mean is, if we look at the first term and then the sum of the first and second terms, that's the second partial sum. And then the sum of the first 3 terms, that's the third partial sum. And we ask, all right, where are these partial sums going? Are these sums aggregating in such a way that they're headed towards a limit? If the answer is yes, then we say that the series converges and its sum is equal to whatever that limit is.
Okay, I think I get it. Now can we look at an example of a divergent series? Is there a go-to example that we should talk about?
Oh, sure. The most famous example of a divergent series is probably the harmonic series, which at first glance looks very similar to the geometric series. So, it's a rather mild-mannered example of a divergent series. And in fact, it's tricky because it looks like it should converge, but it doesn't. So, all right, what is the harmonic series? Well, it's the sum of the reciprocals of the counting numbers. So you want to tell us what you think it looks like?
Okay, well, the reciprocal of 1 it's still 1. The reciprocal of 2 is 1/2. The reciprocal of 3 is 1/3. Oh, I see. It's 1/2 plus a third plus a fourth plus a fifth and so on forever and ever.
Yeah. And if you think about it, the harmonic series contains the geometric series 1 plus 1/2 plus a quarter plus an eighth, etc. So you think, all right, the geometric series converges to 2. So how much bigger can the harmonic series possibly be? I mean, shouldn't it also go to a finite value? And that's the tricky, slippery mystery of the harmonic series. It looks like it should have a finite sum, but it definitely doesn't.
Okay, so a convergent series is an infinite series whose partial sums tend towards a limit. They converge to a particular value. And a divergent series is also an infinite series, but when you look at the partial sums, They don't converge to any particular value. They just grow arbitrarily big. But still, the harmonic series seems pretty different from the one your coworkers were going crazy about at Amazon. 1 plus 2 plus 3 plus 4, all the way to infinity. It's like the 12 days of Christmas on steroids.
Yeah, the infinite days of Christmas.
Remember in our holiday episode when we challenged listeners to come up with a function that could tell you how many gifts were given by a certain day in the song?
Yeah. And you're right. This would be kind of like that, but going on out to infinity.
I remember talking about needing quite a few bird cages when we did that episode.
Yeah, well, I think you would definitely need a lot more now.
Or, according to your friends at Amazon, I could just return 1/12 of a bird cage and then I'd have enough for all those birds.
Oh, yeah, right.
So getting back to that, this 1 plus 2 plus 3 plus 4 infinite series seems pretty different from the harmonic series we were talking about a minute ago. So what's that about?
Yeah, that's a good point. Now, the harmonic series, the terms of that series, 1, 1/2, 1/3, 1/4, and so on, they're getting very small, right? They're clearly heading to 0. So that's what makes you think there might be a hope or a chance that that series will converge. The crazy thing about the series that my Amazon coworkers told me about is it clearly doesn't do that, right? The terms are not going to 0. They're getting huge. So it's like a joke. You're waiting for the punchline because there's a theorem that calculus students learn about that says if an infinite series converges, then the terms of that series must themselves limit to 0. And that's why the harmonic series is tricky. Its terms do limit to 0, but it doesn't converge. When you look at 1 plus 2 plus 3 plus 4 and so on, its terms by no means do they go to 0. So it's clearly a divergent series. And it's like a joke whose punchline you're waiting for. And then when they deliver negative 1/12, you go, the punchline, that's funny. Except they're serious.
I don't get it. What exactly don't you get?
So that's what's so tantalizing about that series.
Okay, but if you take that infinite series of positive counting numbers and look at it backwards so that you're counting down, when you get towards the end of that series, it's like 5 plus 4 plus 3 plus 2 plus what?
You do the hokey pokey and you turn yourself around.
Those seem like they are approaching 0. How's that different?
Okay, that's an interesting question, but let me ask you this. When you turn it around and go backwards, where is your starting point?
Infinity.
That's right. So you just answered the question. You just showed why you can't do that. So there really is a difference between starting in some finite place and heading out to infinity versus starting at infinity and trying to go to 0. Like, where do you go to get started, right? There's no beginning.
That's what it's all about.
Okay, that's a good point. I get it. Now, you mentioned this video that your Amazon coworkers were looking at, and I actually have checked out the same video. It's by a YouTube account called Numberphile, and they went through this entire proof showing how this divergent series of all positive whole numbers adds up to negative 1/12. And I remember that one of the first steps was looking at a different infinite series that was just simply 1 minus 1 plus 1 minus 1 plus 1 minus 1 and on and on and on like that for infinity. So can you kind of explain to us how we would use a series like that to start analyzing the bigger series that we're trying to get at?
Yeah, for sure. And that example, by the way, is also super common in calculus. So you had mentioned earlier that divergent series diverge because they just go to infinity. And that is one of the reasons. This series gives an example of a different reason. So this is an example of a divergent series. And the reason it diverges is because its partial sums continually oscillate back and forth between 1 and 0.
What do you mean by that? What do you mean they oscillate between 1 and 0?
Yeah. So if I just start looking at the sum of the first several terms, the first term is 1. The sum of the first 2 terms is 1 minus 1 or 0, right? The sum of the first 3 terms is 1 minus 1 plus 1. So it's 1. The sum of the first 4 terms is back to 0 and so forth, right? So those partial sums go back and forth between 0 and 1.
Okay, that makes sense. So even though it's an infinite series, what you're saying is if you kind of cut off that series at any random point, if you cut it off after a -1, the partial sum would be 0. And if you cut it off after a +1, then that partial sum would be 1.
Yeah, exactly. And so here, the partial sums don't converge to some limit. This is a classic example of a divergent sequence. It just goes 0, 1, 0, 1, can't make up its mind, right? So in the number file video, they get started with this particular series, and they give us a way to understand how you might be able to assign a meaningful value to it. And so that, I think, is kind of the first step to understanding the negative 1/12 example.
Okay. And what value is it that they assign to this infinite divergent series?
It's not just the number file guys that assign this value to it. It's pretty universally agreed upon that if you were to assign a value to this divergent series, that the value should be 1/2.
1/2? How do they get to 1/2? I could get if it were a 0 or if it was a 1 because it oscillates between them, but 1/2 wasn't even one of the choices.
Right. So if I'm remembering the video correctly, it's like they want to split the difference and take the average, right? So they say, oh, so it can't make up its mind, these partial sums. Do they want to be 0 or do they want to be 1? So let's take the average and call it 1/2.
Okay, that kind of makes sense.
Except it doesn't make sense. I mean, it kind of does, but like even a calculus student is going to go, no, you have to provide some justification for why you're doing that. Because what we don't want to build is a house of cards that is just going to crumble when somebody removes one card from the bottom. We actually need to be building up a meaningful set of rules and processes and so forth. So we need to say a little bit more than that.
And I'm not even sure that 1/2 makes sense because since this is an infinite series of +1, -1, +1, -1, +1, -1, you could really start it at any point. So you could just as easily start it with -1 and then go +1, -1, +1, -1. And if you do it that way, if you start with -1 and go +1, your partial sum is 0. And then you do -1, you're back to -1. If you start with a -1, it oscillates between -1 and 0, and then the average is -1/2. So why is 1/2 any more valid of an average than -1/2?
Right. That's a good question. So one of the names of the game here is that we are stepping slightly outside the normal intuitive realm of arithmetic and making room for some new kinds of definitions to emerge so that we can answer questions like, what value should or could or might we associate to this divergent series? And the answers are going to sometimes seem counterintuitive to us. So yes, if we start with -1 and consider the series -1 +1 -1 +1, notice that that's actually -1 times the original series that we started with, right? It's sort of like you've just flipped the sign of every term. And if you do that, shouldn't you flip the sign on the final answer? So shouldn't the 1/2 become -1/2? I think that's a reasonable property that our divergent series analysis should require.
It's at least as reasonable as saying 1/2 is a proper value for this series to begin with. It's no less reasonable.
Yeah.
than that.
So first of all, the program goes like this. Hey, we're interested in assigning values to divergent series. Why? Because we're tempted. The temptation to do it is just too strong. So yes, that does mean we're going to challenge our intuition, but we're going to find a rigorous way to assign values to divergent series, at least some of them.
All right, lead us through it.
So you and I have been talking about partial sums. Those are the sums where you stop at some finite place, you cut it off, and you say, what does this equal? If I look at the first 12 terms, what does that equal? And then what does the first 13 terms add up to? So what if instead of requiring the partial sums to converge to a value, we know in these cases they don't. So what if we said the average value of the partial sums has to converge? So now we're saying compute the first 3 partial sums, add them together and divide by 3. Write that down. Now take the first 4 partial sums, divide by 4. In other words, take their average, write that down. And now look, where do those averages go? What do I get if I take the limit of those averages? Well, that gives 1/2 for this particular series.
Okay, that's kind of cool. Where did this idea come from? Is this a universally accepted idea in math, or like who started this?
Yeah, this is a universally accepted idea. It goes back to a mathematician named Cesaro, and he came along several decades, in fact, after Cauchy was doing his work defining the ordinary convergence of infinite series. After Cauchy came Riemann, who also had some things to say about infinite series. And then Cesaro came along in sort of the end of the 19th century, and he sort of said, we're going to look at these divergent series and we're going to try something new with them. And so he defined this technique of looking at the averages of the partial sums and asking questions about their convergence. And here's something super cool. Any series that converges in the ordinary sense, like the geometric series that we started off with, 1 plus a half plus a fourth and so on, Cesaro's method will give you the right answer for all of those convergent series, and it will give you answers for some divergent series. So it's an extension of a well-known, long accepted approach. Cesaro extended it, and his approach gives 1/2 in the case of 1 minus 1 plus 1 and so on.
Okay, I get what you're saying now, but now I'm wondering, do we still call the value 1/2 the sum of the series? It's not really a sum in the traditional sense, so do we still use that term?
Yeah, we do, but it depends a bit on context. So technically, we say that the series 1 minus 1 plus 1 minus 1 and so on is Cesaro summable, and its Cesaro sum is 1/2. And you're right that it's not a sum in the usual sense. So we can clarify what we mean by including Cesaro's name. Now, if we're using some other summation technique, say one due to Abel or Ramanujan, we'd call the sum the Abel sum or the Ramanujan sum, etc. But if the context is clear, we can relax a bit and just call it the sum.
Okay, well, if I remember the number file video correctly, once they got to this point where they stated that 1 minus 1 plus 1 minus 1 plus 1 minus 1 equaled a sum of 1/2, after they did that, then they started working with that series and the main divergent series that we're getting towards, 1 plus 2 plus 3 plus 4 plus 5. And they did some kind of arithmetic of taking those two series and writing one on a piece of paper and then writing the second one under it so the terms lined up, and then adding the terms from one series to the terms from the other series to get some result. Are there rules that mathematicians follow when they're working with these kinds of series about what you can and can't do with them and how you can apply arithmetic to an entire infinite series like that?
Yeah, I remember when I watched the number file video, I thought, boy, these guys are kind of playing fast and loose with all these series, but they're doing operations that seem plausible. Let me tell you what those operations are and where I learned about them. So there's a very famous mathematician named G.H. Hardy, who was alive in the late 19th century and up through the middle of the 20th century. And aside from his many significant contributions to mathematics, he's famous for an essay he wrote called A Mathematician's Apology, in which he said, hey, I'm really sorry for all the math I did. Okay, no, it wasn't anything like that. It was a different kind of apology. But in the late 1940s, he wrote a book called Divergent Series. In fact, it was the last book that he ever wrote, and it was devoted entirely to the subject. So this was kind of eye-opening for me, just to learn that there was an entire volume written by a very famous mathematician devoted to divergent series. That's interesting, right? Why would you do that? And in that book, he says, here are 3 rules that seem plausible when manipulating series. Now, before I tell you those rules, do you want to take a guess at the kind of things that would be reasonable to do?
Sure, but can you ask me a question to sort of lead me in the right direction?
Yeah. So we already mentioned that one reasonable property would be that if a divergent series sums to a finite value, call it S, and you now multiply each of the terms of that series by some constant, it should have the effect of multiplying the sum by that constant. So if you multiply everything in the series by K, the final answer should become K times S, right? So that's an example of something that we want. Like if you multiply every term, it should have the effect of multiplying the answer. So along those lines, can you think of any other arithmetic properties that we might want to do?
Well, I was thinking if you take a certain series and you add it to itself, then you will double the sum. You'll get 2S instead of S. But that might just be the same thing as multiplying every term in the series by 2.
So instead of adding a series to itself, what if you took a different series and you added it? Now you've got two different series and you want to add them together. What do you think should happen to their values?
I think if you take the first series whose sum is S and you add it to another series whose sum is, let's say, T, the new series that has all the terms from both series added all together will have a sum of S plus T, right?
Yes, that is the second rule. So the first rule that Hardy mentions is the scalar multiplication. The second property that he mentions is this ability to add two series together. And there's one additional one, which might be a little harder to guess at, so I'll just mention it here. If a particular series has a sum equal to S, and you take the first term of the series and subtract it out from the series, that has the same effect as subtracting that first term from the sum itself. So these are the three properties that we want.
Okay, so then does that mean that if we take a look at the infinite series that we've been talking about that sums to negative 1/12, 1 plus 2 plus 3 plus 4 plus 5, all the way up to infinity, if we take the first term out of that series, which is the 1, and then we just start with 2 plus 3 plus 4 plus 5, all the way up to infinity, now we've subtracted 1 out of that series, so we also subtract 1 from its sum, and so now the sum of 2 plus 3 plus 4 plus 5 and on and on and on is negative 1 and 1/12?
I think the answer is no. That property doesn't apply to every technique of summation of divergent series. Now, the particular series that we're looking at, 1 plus 2 plus 3 and so on, that is related to something called the Riemann zeta function. And from within that context, you can't do what you just asked about. However, there are many techniques like the technique of Cicero that does allow for this operation to happen. So you have to keep your wits about you when you're playing with divergent series. So for the series 1 minus 1 plus 1 minus 1, yeah, you could pull out the first term of that series and subtract it from the answer. And in fact, if you subtracted the first term, what would you get? Let's go through that exercise. So we know the series adds up to a half. If I subtract 1, what should I get?
You should get negative 1/2.
Okay. And if I remove the first term from the series, what does it look like?
It leaves us with that series I was talking about before that starts with a negative 1. It's negative 1 plus 1 minus 1 plus 1. Oh, that's pretty cool. I get it.
Okay. So these two properties reinforce each other in this case. Like, this is the kind of internal consistency that our rules should have. Now, again, you have to be careful with divergent series. And I think the guys in the number file video were reasonably careful. I'd have to go back and look to see if they really nailed everything very carefully. But if we have these rules in hand, then we can actually figure out some pretty cool stuff. Like, if I just throw an example at you, do you want to try and see if we can figure it out?
Yeah, I'd love to. What do we need to do?
All right. First of all, I'm going to ask you to get out a piece of paper and a pencil because I am going to have you write down a couple of things. So while you're getting that, for people who are listening right now, if you want to follow along, you could grab a piece of paper and a pencil too, or you could just sit back and listen to the soothing tones of our voices. That's fine too. But Noah, I am going to make you get out paper because I want you to try this.
I've got my paper and pencil and I'm ready to go.
All right. Here is the series that we are going to try and evaluate. 1 minus 2 plus 3 minus 4, and so forth. I'd like to know, what does that sum to?
All right. So I've written it down as far as minus 6 on my paper. I have 1 minus 2 plus 3 minus 4 plus 5 minus 6, ...
Great. So let's say that that's equal to something. We don't know what it is yet, so let's call it S.
All right, equals S.
Now, we have 3 rules that Hardy told us about.
The first rule of Fight Club is you do not talk about Fight Club.
Rule number 1, you could multiply by a fixed constant. Rule number 2, you could add some other divergent series to this series. Rule number 3, you can peel off the leading term of the series, like you can subtract the leading term of the series and similarly subtract it from the value that we assign to it. So of those 3 particular rules, anything jump out at you?
I kind of think we want to go with the second rule if we're going to actually start manipulating something here. The other 2 rules are just going to change S by a little bit. But if we start adding in a completely different series, that seems more interesting. Like, that seems like it might have a more interesting result to me.
Let's follow your intuition. I think that's good. So, all right. Any thoughts on which series we should look at?
Well, we've had a couple that we've talked about. I'm going to guess that it's either going to be 1 plus 2 plus 3 plus 4 plus 5 plus 6, or it's going to be 1 minus 1 plus 1 minus 1 plus 1 minus 1. Is it one of those 2?
It is.
Well, since I understand the second series a little bit better, let's try that one. Let's try 1 minus 1 plus 1 minus 1. So am I going to write those terms underneath my other series here?
Yeah, line it up exactly.
Okay, so the 1 is going under the 1, and then the minus 1 is going under the minus 2, and then the plus 1 is going under the plus 3, and then another minus 1, and then another plus 1, and then another minus 1, ... And I know that that equals 1/2 according to what we've already discussed. So if I add these 2 series together, I'm going to get 2 minus 3 plus 4 minus 5 plus 6 minus 7. And that's going to keep going like that infinitely. I know that's going to equal S plus 1/2.
Yeah, perfect. You got it. So what next?
I'm not sure what next. Can you give me a hint?
Sure. So look at the new series that you have created. 2 minus 3 plus 4 minus 5 and so on. How does that compare to the series we're trying to evaluate?
Well, okay, this new series is 2 minus 3 plus 4 minus 5 plus 6. So the absolute value of the terms is 2, 3, 4, 5, 6, just like the starting series was 1, 2, 3, 4, 5, 6. It's just that the positive and negative signs in front of each digit has flip-flopped. Instead of minus 2 plus 3 minus 4 plus 5, I have 2 minus 3 plus 4 minus 5. And we've also gotten rid of the initial term, which does kind of sound like that third rule you gave us.
Yeah. In fact, if you took the series that we started with and subtracted 1, then you would be left with minus 2 plus 3 minus 4 plus 5, which is just the flip-flopping of the signs from what we have here. So you're right. If we subtract 1 from the original series, which we're allowed to do, and then multiply the result by -1, which we're also allowed to do, then we get this new series that you're looking at, 2 minus 3 plus 4 minus 5, and so on.
And would that mean that when we start with a series that equals S, and we get rid of that first term, which is 1, that makes the new sum S minus 1, but then we would have to multiply the entire series by -1 to flip all of the signs. So we would get the quantity S minus 1 times -1, which just becomes negative S plus 1, or 1 minus S, right?
You got it. That's exactly right.
But we also said that this new series equals S plus 1/2. So are we saying 1 minus S equals S plus 1/2?
Yes, we are. And that is the equation we need to solve.
Okay, so I'm writing down 1 minus S equals S plus 1/2. And now I should be able to solve that for S. So if I do a little bit of algebra here, I get 1/2 equals 2s, which means s equals 1/4. So
That's right.
So the sum of our initial series, 1 minus 2 plus 3 minus 4 plus 5 minus 6, that all sums to 1/4? It does. Pretty cool. Yeah. And this 1/4 result that we got, it's completely legitimate. The steps that we use to get to it are completely legitimate mathematically. They are, but let's just say a few words of caution here because we are playing with divergent series. So we need to be sure we understand the rules we're playing by. Now, earlier we mentioned a method called Cicero summation, and that technique applies to the series 1 minus 1 plus 1 minus 1 and gives us the answer 1/2. That technique, however, doesn't work on this series. Why not? Well, if you write down what the partial sums are, and then you take their averages, which is what Cicero summation requires, that doesn't converge to a limit. In fact, these partial sums demonstrate an oscillating behavior, and they just never settle down on a particular value.
Settle down, Beaver.
So we need some other technique, and fortunately, we have one, which is due to the mathematician Niels Henrik Abel, and it is named after him, and it's called Abel summation. We're not going to go into the details of how to do that. It's very clever, but that technique extends the technique of Cicero. In other words, it gives the right answer for all of Cicero's answers, and it does even more. It applies to a wider class of divergent series, and that particular technique does give the value 1/4. So we're totally good. Awesome. You know what's interesting, Noah, about this technique that Abel invented is that we are applying it to calculate values for divergent series. But listen to what Abel himself wrote about this. He says, the divergent series are the invention of the devil, and it is a shame to base on them any demonstration whatsoever. Yeah, wow, he really hated those divergent series, didn't he? I know, right? So we've been talking about these divergent series for a while. I'm wondering, now that we've gone through Hardy's rules and we've looked at how to come up with values for the sums of some of these series, do we have enough info to look at that negative 1/12 result and see how the number file guys got it? Yeah, we do. In fact, the approach that's presented in that video is very similar in feeling to the exercise that you and I worked through to derive the answer 1/4. So why don't we step through it and sort of explain how it's presented in that video, and then maybe make a few comments about the viability of that approach. Does that sound good? Okay. So they start with the assumption that the series 1 plus 2 plus 3 plus 4 is summable, and they say, let's call the answer S. Okay. Then, using the series that you and I just computed, where we got the answer 1/4, they perform a subtraction. So they take 1 plus 2 plus 3 plus 4, and so forth, and subtract from it the series 1 minus 2 plus 3 minus 4, and so on. Okay, so just to clarify, when we added two divergent series together, we said that the new sum of the new resulting series would be the two previous sums added together. So I'm assuming when you subtract a divergent series from another, that you subtract its sum from the other series sum. So if 1 plus 2 plus 3 plus 4, etc., is S, and we already know that 1 minus 2 plus 3 minus 4 is 1/4, the new series that they get when they make that subtraction problem should have a sum of S minus 1/4. Is that right? That's right. So whatever it is that we get, we're going to set it equal to S minus 1/4 and then see if we can do some algebra. Now, just like you did with our series, they line the terms up directly one above each other, okay? And that's going to be important for the final calculation that they perform. So they do that. And if you can imagine these two series being written down, or better yet, if you get out some paper and write it down for yourself, you'll see that going down the line, these differences are 0, 4, 0, 8, 0, 12, and so on. So that subtraction problem yields some new infinite series that can be thought of as 4 plus 8 plus 12 plus 16, and so on down the line. Okay, that makes sense. Then what do they do from there with that? Well, do you see any relationship between that new series and the one that we're targeting? Kind of. I mean, these are all multiples of 4. 4 plus 8 plus 12 plus 16. So we talked before about the rule of scalar multiplication. Can we do it in reverse? Can we do it with division? Are we allowed to factor a 4 out of each of the numbers in the series? Yeah, exactly. And in fact, that's what the number file folks do, is they pull out a 4 and they rewrite it as 4 times, then in parentheses, 1 plus 2 plus 3 plus 4, and so on. Wait a second. 1 plus 2 plus 3 plus 4. That's the series we're trying to find the sum of. That's the series that we said is S. So this just equals 4S. Exactly. So what they end up with is the algebraic equation, S minus 1/4 equals 4 times S. And we can solve that. Let me guess. I don't even have to do it. It's going to come out S equals negative 1/12, isn't it? Bam! You got it. That's exactly it. S equals negative 1/12. And so that's how they present it in the video. That is utterly nuts. I love it, but it's utterly nuts. But I have a question for you. Okay, go for it. Obviously, when you add up all of these positive whole numbers, the answer isn't really going to be negative 1/12. So this technique that they used is pretty interesting and cool and gives you a very surprising and counterintuitive answer. But what is it about this technique that you would say works versus what is it about this technique that you would say, it doesn't really work that way? So first of all, we're talking about divergent series and we're assigning values to them. So already we're kind of stretching our mind and expecting some weird things to happen. But before we get to the weirdness, let's just note that there are a few steps in the calculation that we just described, the ones from the number file video, that maybe aren't quite rigorously justifiable. And you'll note that the answer that they get starts out with 0 plus 4 plus 0 plus 8 plus 0. It's got all those zeros interwoven into the non-zero numbers, right? Well, Hardy doesn't have a rule for us that says if you've got a bunch of zeros, you could ignore them and get rid of them. So that's a little bit problematic right there. Okay, I mean, I can kind of see how it makes sense that you can ignore a bunch of zeros in a giant addition problem, but at the same time, I also get what you mean that Hardy didn't provide us with a rule to say what to do in that situation. Yeah, and this is because divergent series don't behave in the arithmetically familiar ways that we would expect. So this is an example of a place where you have to be careful. You would really have to ask, if I threw in a bunch of zeros, like every other term, I inserted a little zero in there, do all of my results still apply or do they break down? And there, the answer has to do with what I would say is the second point I want to make, which is that the number file explanation is intuitively very nice, and it gives us a heuristic, a way to understand what the answer might be. And it happens to produce the right answer. But the actual underlying summability technique is due to something called zeta regularization. And that relates to the Riemann zeta function. And in that video, they say, we're not going to get our knickers in a bunch talking about zeta functions, which, okay, I get that. That's great. But that actually is the real way to approach this result. It does rely on using some pretty sophisticated techniques. And those techniques do not obey Hardy's rules. They're not friendly in that way. So I think we have to take all of this with a grain of salt. But the magic is this fast and loose approach gives the right answer. The answer really should be negative 1/12. And they gave it to us. Okay, but what I find interesting here is that you're saying now that negative 1/12 really is the right answer. And now my brain just doesn't know what to do with that at all. Okay, fair point. So here's sort of the summary view on what's going on with divergent series. Mathematicians want a way to assign meaningful values to divergent series.
The proposition seems crazy and foolish at first, but it turns out to be quite useful, actually. So this is an agenda we want to pursue. It doesn't mean that these infinite divergent series really, quote unquote, add up to the numbers that we're presenting as the answers. Hardy had something super interesting to say, which is that in general, it really seems like there is only one reasonable value to assign to a divergent series. And if you think about it, that's crazy. It's like the universe is saying, yeah, go ahead. You can assign values to these series because, in fact, there's really only one right answer to give anyway. So go look for it. If you find it, fantastic.
I hear you, but this just sounds like magical thinking to me.
Well, what makes it not magical, though, is the rigorous methods that are employed. So we say we want to assign values to divergent series, and there is a very rigorous way to do that. The real question comes when you say, well, what does it really mean anyway? And in the case of 1 plus 2 plus 3 plus 4 adding up to negative 112, it doesn't mean that those numbers eventually are going to add up or get close to negative 112 in any way. And yet, there is a very real sense in which that number, negative 112, is the right number to associate to that divergent series.
Yeah, and I believe that they even mentioned in the video that there are physics equations and physics problems that use that negative 1/12 result correctly to describe actual physical phenomena. So that just blows my mind even more.
I know, I love that. And apparently this divergent series with its sum of negative 112 is important in string theory. It has something to do with the energy fluctuations in a vacuum, and all of that just blows my mind.
I know. It reminds me of something you said very early in the episode where hearing this setup sounded like the beginning of a joke and like you were just waiting for the punchline, and then it comes negative 1/12 and it's like, that's the punchline.
You know, this is one of the things that I just love about mathematics and why it is just so charming to me. And do you remember the episode we did with Dan Finkel about For the Love of Math?
Yeah,
we
sure.
use the word romantic, the romance of mathematics. And for me, there's something about the romance and the magic and the charm that all comes together. And this problem illustrates that, right? Negative 1/12, which is this little weirdo fraction, is on the one hand so clearly not the answer to this problem, and yet it absolutely is. And I love that. I'm here for it.
Yeah, me too. And speaking of jokes, I'd like to remind listeners that we are still collecting jokes from you for an upcoming episode that we want to do all about math jokes and math humor. So Pete, can you tell our listeners how they can send those jokes into us or how they can reach out to us with any other comments or questions?
Sure. My favorite way to learn new jokes from our audience would be to have them use our SpeakPipe page. This is like an old school way where you would call into a show and leave a recorded message, only you get to do it on the internet. So the address is speakpipe.com/mathclubpodcast. Head over to the site, leave us your favorite joke. Let us know if it's okay to put it on air in the show, and we will absolutely do so. You can also send us a joke using our Twitter account. Our handle is @mathclubpodcast. Or send us an email. Our address is mathclubpodcast@gmail.com.
Okay, Pete, I think we're going to wrap this one up because I need to head out pretty soon to get to the Enchantment Under the Sea dance.
The Enchantment Under the Sea dance? Wow. I got to tell you, if I was going to one of those dances, I don't have a thing to wear.
Well, luckily, I have this wetsuit tuxedo that I don't have to return till tomorrow, so I am set.
You really are a right proper gentleman.
All right. Bye, everybody. We'll see you next time.
See you next time, everybody.